So today's notes are really just a recap of our two types of error that we've learned about now that we've talked about Taylor error. So looking at the different types of problems that we have, the actual error that we're looking at with any approximation is not the error bound, which is like the worst case scenario, but the actual error that we get is when we can plug the x value into f of x. So like we can find sine of 0.1, for example, on our calculator. And then we can plug that x value into our polynomial. So maybe we can find p4 of 0.1, whatever, to get that value. And the difference between those two is the error. So we did that on our notes yesterday where we said, okay, it would be like whatever the actual f of 0.1 is minus, let's just say we used a fourth order polynomial, minus that approximation, that's equal to the actual error. And so again, that's actual value minus approximation. So here's another example of that. Let's say our function is 1 over 1 minus x. Generate all these terms. We want to approximate f of 0.1 using a second degree Taylor polynomial. So we could plug 0.1 into 1 over 1 minus 0.1 to see what that actually is, right? Just like we could in our calculator find sine of 0.1, something like that. So here's what we're saying the actual function value is. If we use our second degree Taylor polynomial and plug in 0.1, we're just using the first three terms of this Taylor polynomial, so we get something close. And so the actual error, how far off are we actually, is 1.1 repeating minus 1.11, so that leaves us with 0.00 and then 1 repeating. So this isn't used all that often. They don't ask us about actual error very often because if we have the actual function value, why are we bothering to approximate, right? So it may show up, but more often we use our error bounds, which are like our maximum errors. Okay, so previously we talked about alternating series. Alternating series do show up in free response questions on the BC test pretty frequently, and they're kind of nice to have. I think they're the easier problems to think about now that we've talked about Lagrange error. So if a series is alternating and decreasing, then the error bound, which again is just the worst case scenario, or another way to think of that is like the maximum possible error or maximum possible amount we could be off on our approximation compared to the real thing. It can be found by taking the absolute value of the n plus 1 term, or I just always think of this as like the first neglected term. So for example, here's our alternating series, right? It's a Taylor polynomial, and it has, taken out to n terms. So if our approximation for that function is 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, that is alternating. The terms are decreasing. And so therefore I can say, oh, this is an alternating series. So whatever I use, whatever my approximation is for this alternating series, the error bound will at most be the first neglected term. If I went out to the 1, 2, 3, 4, if I went out to the fifth term here, then the sixth term, the next term in line, is the maximum possible error. So even though it's negative, we take the absolute value and say maximum error is 1/6. Another way we write that is the remainder of, let's see, this was n equals 5. Is equal to, I was trying to look at what our function would be. I'm not going to write an approximation value because I'm not quite sure what we're plugging in, if we're plugging in 1 or what. But anyway, the remainder of the fifth value is equal to the sixth term, is what we're saying. And that's equal to absolute value of all that. That's equal to 1/6. So it's not saying the actual error is 1/6. It's just saying it's at most 1/6. Now, what we learned yesterday was this Lagrange error. So the method uses a special form of that Taylor polynomial formula to find the error bound. Again, error bound is maximum error of a polynomial approximation of a Taylor series. So remember, the formula is really just this part is saying that x minus a to the m plus 1 factorial is saying like that's the next term, but most of the work is right here figuring out what is the maximum value of the n plus 1th derivative. There are a couple of different scenarios that we have. Sometimes this is really easy to figure out if we're looking at a sine or a cosine function, and sometimes it takes a little bit of work of finding patterns, depending on the function. If it's not sine or cosine, I've got to figure out a bit of a pattern. So this z that we're talking about is some number between x and a. Now they're saying a in this document. A is our center. So on yesterday's notes, we said c. But z has to fall somewhere between your approximation x, like what number are you plugging in, and the center c or a. To find that error bound, though, z is going to end up being one end or the other. So to determine whether z will have a value the same as x or a, you just plug each endpoint into the formula you figured out for the n plus 1th derivative, and you look at which one's bigger. So that's what we did yesterday. So here's an example of that. Say we're trying to find the error for a second degree Taylor polynomial approximation of this f of x. Okay, so if I want to do that, if I know I'm using a second degree Taylor polynomial, so I'm using p sub 2 of x to approximate f of x. Right. To approximate f of x, then I have to figure out what the next derivative is going to be. So what is the third derivative, so that I can figure out what that maximum value would be. So they've taken you through that. Okay, here's the first derivative. Here's the second derivative, and here's the third derivative. Now none of these are coming out negative because there's a bit of chain rule going on in here, right? It would be -1 over 1 minus x squared, but they've times the derivative of 1 minus x makes that positive. Okay, so anyway, we've got our three derivatives. And so for this third derivative, I have to figure out, okay, z is some number between the center, which is 0, and it looks like we're plugging, what are we plugging in? 0.1, it looks like. So z is some value between 0 and 0.1. So I just plug in 0 into the third derivative formula and see what I get, and plug in 0.1. Now you don't actually have to find the values, but you're just saying 6 divided by 1 compared to 6 divided by something smaller than 1 raised to a 4th power will be 6 divided by something smaller. So overall, that's a bigger number. If you have a calculator, of course, you might want to calculate it just to double check. So this is bigger. So this is our maximum derivative value. Okay, so back to that error bound formula. Now that we know what the n plus 1th derivative max value is, that goes there. And then it's x minus c, so 0.1 minus 0 to the 3rd power over 3 factorial. And that calculates out to this number. So this is the maximum error. Instead of saying the actual error, we might say something like this. Okay, so f of 0.1 minus my second order Taylor polynomial of 0.1. It's not equal to this number. It's less than or equal to 0.00152. And in the previous example, I would have said, where we had actual error way back in the beginning, that difference, the absolute value of that difference is equal to the actual error. So that 0.001111 repeating, that's the actual error. So that's the difference between these two. On the free response questions, you are most likely going to have some sort of error bound instead of an actual error. So we will be, showing that this error, going through these steps to show that this error would be at most or less than or equal to 0.00152. Now, these are the harder problems where f of x is something that's not just sine or cosine. There is an exception here. When f of x is sine or cosine, life is nice and easy because the maximum value for a sine or cosine function is 1. We don't really care about what it actually is at the endpoints. So like, for example, if that third derivative was sine, and I was saying, okay, sine of 0 is 0. What's sine of 0.1? I don't know, but I don't ever hit 1 between sine of 0 and sine of 0.1. That doesn't matter. We're coming up with like a very conservative, give me the biggest possible error, give me the most room for failure here. So it doesn't matter what your interval for z actually is. That value will always be 1. Okay, so more examples. Find the upper bound for the error of the 5th degree polynomial Taylor polynomial approximation of e. So e is equal to e to the first. So what we're saying is we want f of x is e to the x, and we want to approximate f of 1. It says we're going to use a 5th degree polynomial. So we're going to approximate f of 1 by using the 5th degree or the 5th order Taylor polynomial. Oh no, 5th degree, sorry. Approximation of e, but that is the 5th order for e. And we'll plug 1 into that. So they've done that for you. E to the x is one of the Taylor polynomials that you're supposed to memorize. So just working on that formula, taking it out to the 5th power. The error bound would then be the error bound using a 5th order approximated at 1 would be the 6th derivative of z, x to the 6th, because this is e to the x is centered at 0, so just x minus 0 to the 6th over 6 factorial. So we just need to figure out, well, what is this 6th derivative of z maximum value? Well, you might start taking derivatives and realize that, oh, every derivative of e to the x is e to the x. And if z is somewhere between 0, if z is somewhere between 0 and 1, technically you are plugging in both endpoints and saying, all right, what's bigger, e to the 0 or e to the first? So e to the first is bigger. So this maximum value here, this 6th derivative of f evaluated at z, that has to be e. So I have to replace that with an e. All right, so they've shown you all that work down here. Okay, so we've got the e. What's the x value that we're plugging in? 1, so 1 to the 6th over 6 factorial. So e over 6 factorial. And if we want a decimal approximation for that, that calculates out to 0.00377. So what we're saying is the difference between f of 1, or how about instead of f of 1? The difference between e to the first and my 5th order approximation evaluated at 1 will be less than or equal to 0.00377. That's the maximum amount we can be off. The actual error would be, go ahead and put e to the first into your calculator. There's e. Go ahead and plug 1 and calculate what the Taylor polynomial came out to, approximate e to be, and subtract those values. So this is saying e minus my Taylor polynomial approximation is equal to 0.00162, apparently, if you subtract those, right? And that number is less than our maximum error, so that's kind of a sign that you're at least in the right direction. Here's another example. What degree Taylor polynomial for natural log of 1.2 might have an error less than 0.001? Okay, so first start off with the Lagrange formula that we have. So setting up my formula. And then remember, we have to figure out a pattern. We did this in yesterday's notes, and I think on the homework last night. What is the pattern for the derivatives of natural log of x? So you can see here's natural log of x, take some derivatives. What does the pattern come out to be? Well, the nth derivative is what we figure out first. Now, I don't use the alternating piece because in our error formula, remember, we're always looking at absolute value. But we did figure this out yesterday. We said, okay, the numerators turn out to be n minus 1 factorial, and the denominators are all x to the n. And then remember, the next step is to find the n plus 1th derivative for the formula, which is literally just plugging in n plus 1 into your formula. And again, ignoring that alternating piece. So n plus 1 minus 1 becomes n factorial. X to the n becomes x to the n plus 1. Okay, so we still have to figure out what is this max value at z. So we have, let's see, we're looking at values between 1 and 1.2. So this might be explained in this paragraph, but remember your next step is to say, okay, z is between 1 and 1.2. So n factorial over 1 to the n plus 1 would just be n factorial over 1. N factorial over 1.2 to the n plus 1. That has a slightly bigger denominator, and so that will be smaller overall. So the larger one is the n factorial over 1. So into your Lagrange error formula is just, this is getting kind of messy right here the way they're showing it, but I would just say, I'm going to simplify things a little bit. I'm going to say, okay, so my formula is, I'm going to kind of pick it up from right here, I think. My formula is n factorial, because that's what f to the n plus 1 of z is equal to, times 1.2 minus 1, x minus the center, to the n plus 1 power, over n plus 1 factorial. Okay, so, and I'm just using, where is it? I'm just filling this in. I figured out what the max derivative was. And then we did this yesterday. How does that simplify? Well, and that's what they're showing in this step. Simplify things. N factorial over n plus 1 factorial is just 1 over n plus 1. This z is not here. This is a 1. We figured that out. 1.2 minus 1 is 0.2 to the n plus 1. So fully simplified, it becomes 0.2 to the n plus 1 over n plus 1. Figure out when that's less than 0.001. Now they say use trial and error. If you have a calculator, you don't need trial and error. You type this into your graphing calculator and then look on the table. At n equals 3, we get a value that is less than 0.001. All right, so this was just a recap of what we talked about yesterday. Maybe seeing the notes in this format might make some things click, but there is definitely a process to figuring out Lagrange error. And like I said yesterday, we are very likely to see either this Lagrange error or a nice, easy alternating series error, where it's just the first neglected term. Where did that go? This. On the AP test. So we are going to be doing a lot of free response practice prior to taking a test over all this stuff. Your homework tonight is this remainder theorems worksheet. All right, so work on this. I will post the answers and we will go over it during our next class.